Hello, this is Ryan Smith from RHK Technology. I'll be hosting today's webinar session on how to tune a PLL for non-contact AFM using R9. Our speaker today is Dr. Steffan Porthun, who is a scientist with RHK Technology, specializing in the development of the R9 functionality, and in this case we'll be presenting this topic. We're going to have a presentation on this functionality on how to tune the PLL, and at the end of the presentation there will be a time for a question and answer. There is a question tab on the GoToWebinar control panel that will allow you to type in your questions, and those will be shared with Steffan and the answers provided. And throughout the presentation, all attendees will be on listen-only mode, so we will gather the questions and use them at the end of the presentation. So at this time, we are going to begin the presentation, and we look forward to your questions, and thank you all for attending very much.
Hello, my name is Steffan Porthun. I was involved in developing the RHK R9 SBM controller. This webinar is about the tuning of the different control loops of our controller. Let me give you an overview of this presentation. We will start measuring the resonance. Then I'll show you some artifacts of resonance curves, things that you need to be aware of, things that show up in resonance curves that are a clear sign that something is wrong and needs fixing. Once we have talked about that, there will be a section about phase loop tuning. Then we'll talk about the amplitude loop, and in the end we will say something about the Z loop tuning. Let's start with the resonance measurement. Before we can set up anything on the microscope and on the cantilever, we first have to measure the resonance peak. This is done with a frequency sweep panel that you can reach via the spectroscopy menu item and then frequency sweep. This opens, and here you see two plots. The top one is the amplitude, the bottom one is the phase, and they're plotted over frequency. Here on the right side you see a number of parameters that are used for the sweeps. There are two types of sweeps. The first one is the coarse sweep, and then the coarse sweep allows us to find a resonance peak in a big frequency range. It quickly goes through the range and drives all the frequencies in there, one after the other, and whenever the frequency rings the cantilever, there will be some oscillation, and the oscillation will be visible here, and this allows you to quickly find the peaks. You set the start frequency, the end frequency, and the step size. Don't make that step size too small, otherwise the sweep will take forever. We want a quick sweep, so we are choosing 15 kilohertz here. Now if I press coarse sweep, you will see that it shows in the amplitude plot, it shows the resonance. In our case here, it is close to 2 megahertz, and there are some harmonics, some higher modes visible here. In the phase plot, you see a strange slope. Note that this is minus 180 degrees, and then it continues at plus 180 degrees. It's a phase graph. And it continues to have the same slope. This slope is caused by delays in the preamplifiers and in the microscope. It is something that you usually only see on very, very big frequency sweeps. You can compensate for it, but it's in the small range that we're working here, a couple of hertz around the 2 megahertz. This will not be a dominant factor in the measurements. Many cantilever manufacturers specify their cantilever resonance frequencies quite well, so there isn't really that much of a need to sweep over such huge ranges as I've just shown. To show you a smaller coarse sweep, I'll change this to 1.9 and the end frequency to 2.1 megahertz, and we'll go for a little bit smaller step size of 1 kilohertz here, and then the coarse sweep will look like this. We're much further zoomed into the peak. You see the face, shoulder here, as you would expect from theory, but there is still a phase wrap in here. We'll get to that later. For now, there's 3 cursors. There's the green cursor, which is on the left side. There's the right cursor, which is on the right side. The red cursor, which is on the right side. And the blue cursor automatically gets set to the top of the resonance peak. So we'll use the red and the blue and the green cursor now to zoom in here. Don't be shy and make it narrow. It saves you waiting time on the measure peak. The start and end frequencies are set here, 1.997 and 2.001. And the sweep time can be set with the expected Q. I usually set the expected Q way lower than the real Q that I expect because the measurement goes faster that way. So if I do measure peak, it takes a little bit, and then we'll sweep through the peak between the 2 cursors. At the top peak position, the blue cursor will show up. It'll automatically get set to the top peak position. And we might see a phase wrap here. Yes, that was the phase wrap. The phase wrap here doesn't really hurt us that much because our operation will be in here. I think we should zoom in a second time, just from here to here, which would make the phase wrap disappear. And now we can go from one step in the Q factors higher. And here's our peak. This looks pretty good. So when we're happy with this, we can use the resonance, the peak frequency that we determined here, which is 1.999877 megahertz. The amplitude is 16 millivolts, and we have a Q factor of 40,000. If we press the set frequency button here, then our resonance frequency will be copied over to the main panel, to the PLL panel, and also our phase offset will be added into that phase offset there in order to make sure the PLL operates at the set point of 0. This is the point where we will operate the PLL, and our phase is already compensated so that the phase angle here is 0, so we can put the set point in the PLL to 0 degrees. Now that we have measured our peak and plotted it, we have one more thing to do before we can actually start tuning the PLL. It's a one-time thing, but in order we have to make sure that the PLL range is actually wide enough to cover the range of the peak. So in order to do that, we have to look into the engine compartment, click at the PLL here, shift all the way over to the right. There is a DF gain. This is actually a bit shift inside the FPGA that tells where the 32 bits frequency bus will be connected to the internal 48-bit frequency bus. In my case here, it is 1.53 kilohertz. You can choose a number of values. What value you choose doesn't really matter. You basically benefit the width of the delta F range over the bit resolution of the delta F word. I think 710 nanohertz are astronomical for our case here. So I could use a 1.5 kilohertz or 3.5 kilohertz. If you have a very low Q factor, then your resonance will be much wider, and you might have to change this to 48 or 24 kilohertz depending on the Q factor. What you want is this phase curve needs to be within the range. If there's any weird peaks or dents in here, you might want to exclude them. This is the way to do it. You only have to do it once for one type of cantilever. This is not very critical. This setting does not affect any kind of gains. It's all compensated for. So whatever you set here is a one-time thing, and you'll never have to touch it again. But the first time you should look at it. Before we can set up the PLL, something else needs our attention, which is the filter control. Inside the lock-in that's put into our PLL loop, there is a filter that cuts out higher unwanted frequencies. This filter determines our maximum bandwidth, and in order for it to be most efficient, we need a 6 dB per octa filter, and we should use filter cutoff frequencies between 500 Hertz and 4 kilohertz. This is a prototype of a 6.0 version of R9S. In the 5.0 R9S, you can select the filters. Also there, you should use a 500 Hertz, a 1 kilohertz, or 2 kilohertz, or 4 kilohertz filter of first order.
Another artifact is crosstalk. By crosstalk, I mean that the cantilever drive signal somehow, capacitively or inductively or however, couples over into the detection signal. So crosstalk is any signal that reaches from the drive signal line over into the detection signal line without having the resonance of the cantilever. So if you think about it, there's now two separate signal paths. One signal path goes from the drive line via our crosstalk path to the detection at a certain phase shift, and the other is the signal path that we want, that's actually driving the cantilever, detecting the cantilever, and then going to the detected signal line. In order to show you this effect, I start up with a nice 32 kilohertz cantilever resonance. There's very little crosstalk. You can recognize crosstalk by an overly high amplitude far out of the resonance. When we're far away from the resonance, then the only contribution on the signal will be the crosstalk. The resonance won't ring, so there's no signal from there. Far away, it's only crosstalk. So if you do your peak search, and in the peak search you already have significant signal, then you have most likely a problem of crosstalk. Here, the crosstalk is way less than 10%, or this is not even crosstalk because we're quite close into the resonance of the cantilever. The amplitude you see here already has to do with the resonance of the cantilever, but this is less than 10% of the cantilever resonance, so this won't matter. We have a nice phase curve that goes from a little bit higher than 90 degrees to a little bit lower than minus 90 degrees. I've already explained that these are shifted. artificially. So this is about 180-degree phase range from here down to here. This is a nice phase curve, everything looks right. Now one thing I can do is I can artificially add a signal to the detection that has a certain amplitude and a certain phase shift. What I've done is I've added a 0.707 millivolt signal of 45-degree phase shift to the amplitude. So now we have two signal paths. One is the crosstalk and the other one is the amplitude resonance. And now our nice amplitude resonance will look like this. The phase turns into a peak, and the amplitude resonance is kind of unbalanced, and you see that the signal here actually drops before it goes into the resonance. There's a minimum right here in front of the resonance peak. That is something very suspicious. This is usually where the detected signal of the two paths cancels each other out, or partly cancels each other out. You see these drops here. That's always a sure sign of crosstalk. Now this is a very dangerous situation for the PLL because our phase range is greatly reduced. If you play with this a little more, you get the right amplitude a little bigger, the phase a little better, then your phase will suddenly look like an amplitude peak, and your amplitude peak will suddenly look like a phase peak. The thing is, if you accidentally your phase hops over this peak here, then on this side the polarity of your phase feedback loop will be inverted and your phase will wander away. The same here. If you go beyond this peak, your phase will wander outside of the picture. So the frequency control loop is only stable between here and here, between those 2 points. And as the phase gets the phase range here from plus 50 to something like minus 50 gets smaller and smaller, your catch range for the PLL gets smaller and smaller. This is very dangerous and can lead to tip crashes. Another example is I've deliberately chosen a crosstalk signal that cancels out here at this frequency. You see that the amplitude is exactly 0 there. At this point, the phase will change polarity. The reason is not a phase wrap, because we're not at 180 degrees here and there. It's just that the amplitude is 0. Then with the 0 amplitude, the noise in the phase is quite high. And then we start with an inverted phase here again. So until here, the resonance is the dominant factor. Behind here, the crosstalk is the dominant factor, by the way. So again, here we see a greatly reduced range in frequency, in phase. It's not as bad as in the previous example, but still very worrisome. Probably you could run the cantilever at this resonance still with this much crosstalk. Now if we increase the signal, I've just taken the same phase as in the previous example and increased the amplitude by a factor of 5. Then we get this dent for the phase. Amplitude has a dip here. Some people call this anti-resonance, and I've heard people referring to this as an anti-resonance of the cantilever. In all cases that I've seen so far, this could be explained very well by crosstalk. Here, this is again quite dangerous because as soon as your phase control hops over to this side, as soon as we get beyond this point, the phase will run away out of the picture here. I'd like to draw your attention to an artifact that's called 1F peak. You might remember this equation from high school math. There's a cosine x multiplied by cosine y equals 1/2 of cosine x minus y plus cosine x plus y. This is a very fundamental equation in all kinds of radio receivers. It talks about mixing frequencies. What we do here is we have our cantilever oscillation signal that we get from the detector. It's in a Fourier transform plot, with where this is the frequency, you would see just one spike here. That's our cantilever oscillation. And we multiply that with our reference oscillator. This is basically what comes from the drive frequency in the figures that I've shown you in the first section. In our case, they are both F0, so X and Y are the same. So they cancel out. The frequency terms cancel out here in this term. So there, the result will be a peak at zero frequency, or DC, which only shows the magnitude of our signal and the phase shift. This is what's used by the lock-in for detecting magnitude and phase shift. But also there is a term of double frequency. Remember, our two frequencies are the same, so this will be 2F, 2F0, and that will be this component. So according to this equation, if our cantilever oscillation gets multiplied with a reference oscillation of the same frequency, then we'll get half of the amplitude in a peak at 0, and we get half of the amplitude and a peak of 2F0. Now every lock-in has a filter to cut this away. So there will be a low-pass filter in the lock-in, I'll get to that a little later, that cuts this peak out, and then we only remain with this one peak that shows us amplitude and phase of our detected signal. So this is basically the theory of mixing. Now we're getting to the artifact. And the artifact is if you have a DC offset here, which you can quite often get due to uncompensated temperature drifts in the input electronics, due to drifts wherever, then this DC offset will be multiplied with our reference oscillation, and that will create a peak at F0 at the resonance frequency of our cantilever. This is a static DC value. This is an oscillation with amplitude 1. So the amplitude of this is DC offset multiplied by, well, sine omega t is the oscillation. So DC offset is the amplitude of this peak. If you're measuring small signals on a big offset, this can be a substantial peak, and it's much further into our DC value than the 2F peak. It's halfway there, which can cause trouble during filtering. So this is again our half amplitude sine phi signal at 0. This is the 2F peak, and our DC offset 1F created 1F peak, and we're multiplying this with a filter. And frequency domain, the filter has a gain of 1 for low frequencies, and then the gain will be reduced all the way down to 0. And then the result of the multiplication will be that the 2F component is pretty much gone. But if our filter is not sharp enough, then the 1F component will still be there, and it'll significantly contribute to our signal. And it will be a noise, it will be an oscillation. What you will see in your signals is an oscillation there. And that's what I'd like to show you in some examples on the real world. I just needed this to explain why this all happens. In order to demonstrate the 1F peak effect, I have rigged up a quartz tuning fork on a prototype R9 system, which has about a 10 millivolt input offset at gain 1. You can see here in the spectrum analyzer already that there's a substantial peak at 2.6 kilohertz, 2.765 kilohertz. You might be surprised to see that our 1F peak shows up at 2.5 kilohertz. The reason is that the PC, the data that gets sent to the PC, has a sample rate of 10 kilohertz or 10 kilosamples per second. Internally, the R9 runs at 200 kilosamples per second, and the data that goes up to the PC is decimated. This is an effect that's only shown on the PC, and nevertheless, we'll be able to judge whether the peak is still there or disappeared. The peak is at 32 kilohertz. Now, the first remedy that we can come up with is compensate for the offset. But before that, I'd like to change the gain to a gain of 8, because we don't use all the input range anyway, and this already reduces the amount of noise dramatically. Now the next thing to do would be to reduce the offset. Of course, we need to enable the offset also. Okay, you see that our noise is already reduced a lot. In order to show this on the spectrum analyzer, I'll stop it and start it again. It's quicker than building up all the averages. You see that our peak is disappeared between the sidebands, which are 50 Hertz separate, actually. Now, if you want to get rid of the sidebands as well, what needs to be done is reducing the cutoff frequency to 1 kilohertz. After that, the spectrum will look like this. And if we want to get rid of them completely, we change the filter to 12 dB per octave. And the only thing left is the two main sidebands, and they are lower than the noise here. So I don't think they matter much anymore. This can be done in principle and on any cantilever microscope with a resonance lower than 100 kilohertz. If the resonance is above 100 kilohertz, then the R9 has an FIR filter that takes care of this 1F peak, and you don't have to worry about this then anymore.
The first PLL PI controller loop that we will tune is the frequency control. The frequency PI controller holds the phase of our oscillating cantilever at 0 degrees, and we will change the set point every 20 milliseconds by 10 degrees up and then back to 0, and watch the behavior of the PI loop. What you will see is as the phase goes up and down, also the frequency will go down and up. So with a 10 degree phase angle set point, our frequency will hop down some degrees, and then as the set point hops back to 0, our frequency will also hop back. And we will look at the hopping back and forth on an oscilloscope. In order to do that, we first need to open the oscilloscope. Here it is. And make sure we're looking at delta F in the top and at the phase in the second. Don't look too much at these two. We'll get to them later. In the layout, you can select what range on the x-axis and y-axis you want. I've set the delta F and the delta F to automatic and the X scale to automatic, and the phase I set to between a small negative angle and 11 degrees, because we're expecting our phase to go up and down from 0 to 10 degrees, so we can nicely see here 0 and 10 degrees. As we start the oscilloscope, we see that the phase is nicely around 0. If it is not around 0, you should change the frequency, but be careful, you get the single hertz digit or the tenth of a hertz digit. So this is 1.999 megahertz. So the 8 would be the single hertz. The 9 would be the tenth of a hertz. So if I change this up and down, you can see that the phase can be set to 0. Whether you need the tenth of a hertz or the single hertz digit depends on your quality factor. You'll have to figure that out. So our phase is nicely at 0. With the phase at 0, we can switch on the PLL. The PLL will try and keep the phase at 0 degrees, and it will do that by shifting the drive frequency up and down. Now the PLL is running. As you see, we have a 100 microhertz noise on here, which is really, really low. The reason is that I set the PI gain value to a really, really low value of 1 millihertz per degree. I did that because I want to show you how a way too low PI gain value looks like. If we now switch on the frequency tune, you first see how the delta F creeps to the new average value, which is somewhere around 5 hertz, because half of the time we're at 0 hertz and half of the time we're at 10 hertz. And we get this pattern. And this pattern is basically the proportional gain and the integral gain hops when the set point hops up and down. You don't see anything on the phase yet because our gain is way, way too low. Now, a good starting value for the gain is always the resonance frequency divided by 100 times the Q factor. Resonance frequency is 2 megahertz. 100 times the Q factor is, our Q factor is 40,000. So this would be 4 megahertz. If we divide that, we'll end up at 0.5 hertz or 500 millihertz. If we set our gain to 500 millihertz, we can see that something is happening at the phase already, and also something is happening at the delta F. Now you might think that this is the optimum value because the delta F, let me tune this a little bit, the delta F looks pretty square, but the phase is not square at all. What we try to do is get the phase as square as possible. There will be peaking at the delta F. I'll explain that a little later. This is a good starting value, but it's still way too low. If I increase it, you see that in the delta F, we'll get some peaking, and our phase will get sharper and sharper. If I go back to 0.5 hertz per degree, and we stop the frequency feedback tuning, you see that our noise here is about 20 to 40 millihertz. If we tune the gain to 2.5 hertz per degree, or even higher, 3, like this, then our noise will be somewhere around 1 hertz. So there is a trade-off between noise on the delta F and steepness of the phase curve in your interface test. The calculation that you should do is you have a certain number of pixels per image scan line. There's a certain scan line time, and within that scan line time, the PLL should be able to respond to the number of pixels inside the image. Otherwise, you see mostly PLL behavior. And so this is basically what you have to tune for. In my case, the 9 hertz per degree, I think we can tune this further. If we go above 14, 15, you see a tiny little spike here. That's bad. That spike means we have ringing. If I zoom in here, you see there's some overshoot, and we want to avoid that. Oops, it's running out of the image here. We want to avoid that. So this is the optimum that you can get, somewhere around 14, 15 hertz for this type of cantilever. You see there's these spikes on the frequency. The reason for the spikes is we're actually comparing two phases to each other. Our phase, our PLL phase is actually the difference between the drive phase, the momentary phase of the drive, and the momentary phase of the detected signal. Those two phases actually turn around all the time, but the difference pretty much stays the same. Now, with this PI controller, we're commanding the receiver phase to be at the detected phase, at the drive phase, or behind the drive phase. So in order to catch up, the frequency on the drive needs to speed up, and in order to go behind again, the frequency needs to slow down. So that's what creates these peaks. The peaks are not really a measurement effect, they're mostly an artifact of what we're doing here. If I zoom into this, you see that there is a step also on here, and that step is something like 4 degrees, is what you would also see from here. There is some, no, there's a step of 4 hertz, and the 4 hertz is what you would also see somewhere in here, this range on the frequency scale. Once we've set up everything, we can switch off the frequency feedback and have a look at our noise figures here. So in our case, the delta F noise is about 1 hertz, but we have a PLL bandwidth of about 4 kilohertz with this now. The next thing we configure is the amplitude control loop. In order to do that, I strongly recommend switching the lock guard on. Lock guard protects us against an invert drive. In order to control a high Q cantilever in ultra-high vacuum, it is sometimes necessary for the control loop, for the amplitude control loop, to actually invert the drive in order to stop ringing. This feature is very useful in ultra-high vacuum, but can sometimes lead to an inverted amplitude control loop, which drives the cantilever at full amplitude, which might damage your cantilever. In order to protect that, we've put in the lock guard. If we switch it on, make sure the maximum phase deviation is set to something like 40 degrees. Maximum dphi over dt can be at 1 megadec. That's fine, it's not that critical. Now, next thing, we switch on the amplitude control loop, and we see a drive amplitude here. In our case, it's around 1.2 millivolts. And we see some detected amplitude, which is something like 16 millivolts, where the set point is set to 16.25 millivolts. Again, for this test, we will set the set point up and down by 1 millivolt. So right now the set point is 16.25 millivolts. It'll be kicked up to 17.25 and then back down to 16.25 millivolts. And this happens every 20 milliseconds. I have set a particularly low PI gain value just for demonstration. This will look like this. Just like in the frequency control, we see the action of the P and the I control here. We're way far away from a good control. We don't reach set point here at all. This is a way too low PI gain value. A nice PI start value, a PI gain start value, you can find by just taking the inverse of the signal to drive ratio. The signal to drive ratio you find after the frequency sweep, it's 13.4. If we invert that, 1 divided by 13.4 is 74 milli. So if I set this to minus 74 millivolts, we get a much better looking drive amplitude and detected amplitude. Make sure that the gain value is always negative here. The reason is if our measured value is above the set point, that means the amplitude is too big, we need to actually reduce the drive. That's why this gain is negative. Here you see a fairly steep drive amplitude change. And you see the shark fins again, just like pretty much exactly like in the frequency control, you see the shark fins again. This is not the optimum gain value. You will have a quite low noise here, but the gain should be improved or increased or actually decreased, so we get a more rectangular shape in the detected amplitude. So make sure you get the right direction here. Actually, the arrow down will increase the gain. It decreases the number, but it increases the gain. So this looks much better. We're at 1 volt per volt, but still it's a little bit rounded. You can get a little bit more. You should tune the amplitude control to about the same rise and fall time as you did with the frequency control. So this is at 1.5. This is pretty good. Maybe 1.4. If you go too far, you see ringing again. That's here. If you go too low, you see the shark fin rounded edge again. So somewhere here around 1.1, 1.2 should be the optimum value. Okay. At this point, we have the PLL set up. It's running the frequency control nicely. You can check this again. And it's running the amplitude control nicely. So everything is set up, and we are ready for a Z approach. The last section of this webinar will be about tuning the Z loop or the topography loop. Finally, we use the Z or approach motor to approach the tip into the sample. You should start with a low Z gain, preferably with a big bias voltage between tip and sample. This way the detection system has time to see the sample early and make a soft landing. Once you're in the vicinity of the sample, I recommend that you do a delta F versus Z curve. This allows you to choose a delta F set point that the system will work on then. The delta F versus Z curve looks like this. What you do is you pull back the tip to a certain distance. In this case, it's 500 picometers, and disable the Z feedback loop. And then you sweep the tip in a controlled way into the sample. And while doing that, you measure the delta F signal. The closer the tip gets to the sample, the more interaction you get, and the more delta F, the delta F signal will drop. At a certain point, this will turn around. You don't necessarily have to go all this far. This is called the repulsive regime of interaction. Most people measure here. You can measure here, but you need some experience to do that. You will have to choose a set point somewhere here along the curve of delta F. In this case, if you set your set point to minus 60 Hertz, it will operate here. And then run the machine there. The interesting thing about this delta F versus Z plot is that it's not a straight line. The slope is very different here at the top of the curve than here at the bottom. This somehow also depends on your sample. This makes it very difficult to predict a gain for the Z-loop, because the gain has to be different, has to be lower here where the slope is steeper, and has to be higher here where the slope is more shallow. The gain is nonlinear, so if you later on, if you go closer to the sample, you might have to reduce your Z-loop gain. Now that you have decided about the delta F set point, we start setting the gains for the Z control. The gains are specified as INP directly, in contrast to the amplitude and phase controllers. We use the INP gains directly here. Most of the gain will have to be integral gain. Some people set the proportional gain to about 1/1000th of the integral gain. This can speed up the loop. This depends on your microscope. It's not a given, but it's something to experiment with. The way to tune the gain is to start to engage the loop, obviously, and start scanning and watch the image line, watch the image. If you increase the integral gain, then your detail will increase in the picture. And if you increase further and further, you get more and more detail, and suddenly the noise will increase. And you want to be at the point where you have maximum detail with minimum noise. Sometimes it's also useful to scan over atomic step edges in order to judge the performance of the Z gain. You should keep in mind while doing this that the Z gain, as I said earlier, depends on the set point. If you increase the set point, you most likely have to decrease the gain. This concludes my webinar. We will have a question and answer session after this. So far, I thank you very much for listening in, and I wish you nice images and good scientific results with our R9 equipment. Please feel free to ask questions right now after this. Thank you very much.
There is a question about the lock guard feature. They're looking for a little more explanation on how this works, and does it need adjustment if you are using a standard silicon cantilever versus qPlus cantilevers?
The question has two parts. Part one is about the workings. What we'll do is internally we watch all the time in a hardware watcher inside the FPGA. We watch all the time the phase signal. When the PLL unlocks, then the phase will deviate from the set point. Normally the phase PI controller keeps the phase at set point, which is 0, as you've seen in the webinar. When it deviates, then that's a sure sign that the PLL is unlocked. So we're watching the phase signal, how close it is to the 0. You can set that on the PLL panel. There's a setting where you can set the phase margin for the lock guard. There's another test, and that test basically checks the value of the phase and basically calculates a slope in the phase by subtracting two subsequent samples inside the FPGA. If that slope exceeds a certain limit, then also basically an alarm is pulled. So these two trigger signals pull alarms, and when these alarms then the first thing that happens is that the scanning freezes, and another thing that happens is that we are pulling back the tip a little bit by some nanometers. And then there's a whole procedure that gets run through that tries to get the PLL into the lock again. And it checks whether it is successful. And in the end, when it's successfully locked in the PLL again, then it engages the tip again and continues scanning. If it cannot successfully get the PLL locked again, then the scan will be aborted. The parameters that you can set are these, is obviously the limit for the phase. The other parameter is this mega degrees, which is basically the difference between, it specifies the difference between two samples on the FPGA. Those parameters, I think they're pretty much the same. It doesn't really matter that much what cantilever you use. There is a phase and there is a phase margin that needs to be watched. I don't think it requires much settings. You can, if it unlocks too frequently, then you can set the phase margin up a little bit. If you have rough samples and PI controller has a tough time, you can increase that limit a little bit and make sure, and thereby make it still keep lock. But that's all. It more depends on your sample than on the cantilever.
Okay, well, thank you, Steffan. We do have another question about what does the unwrap win and how do you apply it?
Yes, the problem with this is that in the controller, all the phases are relative. We're measuring the difference in phase between the drive and the detected signal. That's actually our phase signal. So there are long cables that have phase shifts, but those phase shifts are constant. So there's always an offset on the phase. If this offset is in the wrong position, then the phase will wrap around the bore boundary of minus 180 degrees to plus 180 degrees. And that is what we call a phase wrap. We compensate for that by basically putting the peak of the resonance, which is usually the spot, the peak of the amplitude resonance is usually the spot where the phase curve is halfway between the top and the bottom level. And we at the peak, at the amplitude peak resonance, that phase value basically subtract as an offset from the phase, and that makes the phase plot nicely and without wrapping. That's what this phase wrap removal does.
Can two PLLs be set up to do frequency modulated KFM measurements? And the second part of that is, how would you tune one PLL for the mechanical oscillation and one for the electrical modulation in multi-frequency measurements?
For Kelvin probe microscopy, we usually use a PLL and a lock-in in parallel to the PLL. This lock-in will follow the resonance frequency of the PLL at an offset. If you do that, then you detect the frequency intermodulation between your bias AC drive and the cantilever resonance. There will be some sidebands around the cantilever resonance peak, and we're detecting those sidebands with another parallel lock-in amplifier. I think there is manuals on how to do that. I think going through all this discussion, going through all this in full detail is probably a little bit too far for this webinar. If you want, you can contact me. My name is Steffan Porthun, Porthun at RHK-tech.com, and we can discuss it then there offline.
It looks like we have one more question right now. Can the R9 PLL be used with Colibri sensors?
Colibri sensors, as far as I know, have quite high resonance frequency. I'm not exactly in the picture, but we can drive cantilevers with, or Colibri sensors with resonances up to 15, 17 megahertz. That's not the problem. The problem is maybe how the phase resonance will look like. If the phase resonance and the amplitude resonance looks like the the ones I've shown you in the plot, then there should not be a problem to run the Colibri sensors. I'm not aware of anybody that has done this, but I don't see a problem there.
Okay, there's a question. What range of Q factors is ideal for our PLL? Is there a Q factor that is too low to image stably?
No, people have used the R9 PLL with Q factors of 200,000 and more, and that works fine. Other people have used the R9 with Q factors below 1. That also works. It's very different in setup because the resonance peak is much wider for a low quality factor, and you have to set this delta F range, as I explained it in the webinar. You have to set that differently, and you have to tune the gains differently, of course, but basically it's the same procedure for setting things up, and it should work the same, yes.
Okay, there's another question. What kind of qPlus or tuning fork cantilever has 2 megahertz resonance and I believe 40,000 Q factor?
Yes, this was not a cantilever. This is done on a test unit with my test rig, which uses 2 megahertz quartz crystal. It's much quicker to demonstrate the setup procedure on this, but it works just as well on a microscope. There's no difference in the procedure of setting things up. It's just for convenience, I use this 2 megahertz quartz crystal.
Okay, we have another question. Is there a way to reduce lock guard unlocking with rough samples? Slower scan speed won't help.
I am not sure I completely understand the question. What I understand is that you have a microscope that tends to unlock. If that happens, you can do two things. You can slow down the scan speed. You can reduce the interaction between tip and sample by using less delta F set point. Change the lock range. You might remember in the presentation I showed the lock range, which was 40 degrees. That means that the lock guard triggers an unlock event if the delta F goes more than 40 degrees away from set point. If you set this number higher, then the lock guard will become less sensitive, but there is bigger risk for damaging your tip then.
Another question, with using lock guard, does that prevent snap to contact or jump to contact with cantilever-based non-contact AFM as opposed to, assuming qPlus or one of the tuning fork-based?
The problem with cantilever-based non-contact AFM detection, as you describe it, is that the cantilever constant is not as high as in a tuning fork, and if the force derivative above the sample gets bigger than the cantilever constant, then the cantilever level will snap into the sample. Lock guard cannot prevent this. It just detects it and acts on it. It will stop the scan, it will pull back the cantilever, and then try to relock the PLL, and if the PLL relocks, it will engage it again and continue scanning. So lock guard is a detection, and it acts on the event. It cannot prevent the event. It cannot prevent the snap-in. The snap-in is caused by the cantilever being too soft. There's nothing you can do, I think, about that, other than taking a harder cantilever.
We have another question. This one is about your...
I don't see any further questions coming in. So, Steffan, I want to thank you very much for presenting today and for all of our attendees for joining us. We look forward to seeing you at future webinars.
Yeah, thank you for watching, everybody.
Have a good day.